Hello and welcome to Young Minds versus Physics. Yes, today we are going to discuss about electric field. So let's divide the electric field concept into two parts, and today we shall complete part 1. Okay, and if any one of you have not yet subscribed, please subscribe to the channel so that you will know you will get the notification of the videos that you are getting, and you will be able to watch all the videos related to 11th and 12th standard, and these videos will be helpful for you to give the proper conceptual approach in solving the problems. And if you are aiming for MSET, NEET, or IIT, JEE, right, for all this, these videos are going to help you a lot. Right, so now jumping on to this, right, starting the concept of electric field. Yes, we know the definition, like normally, what is a field? It is the space around, right? It is a space around a charge where its influence is felt, right? And that is what we call within the vicinity of that one, right? And now when we talk about like a positive charge or a negative charge, so then definitely the field extends till infinity. So theoretically talking, we say that field extends till infinity, and at infinity it becomes zero. Of course, but the intensity of the field reduces, right? It decreases. The intensity of the field decreases as you are going far from the charge, right? So now how to understand this field? So it is something like which is invisible, right? And thus to understand field, we take the help of field lines or electric lines of force. So both ways we can we can call them as either electric field lines or electric lines of force. These lines of force, right, they can be straight lines or they can be curved lines. Like these are the lines which represent or which show the path of an isolated or a free unit positive charge, which is left free to move in the field. Like suppose we have a positive charge, and around this there is electric field. Around this there is electric field created, right? So now, so how to understand this field is like what will be the behavior of the field, that can be understood by the field lines. Okay, that can be like, how are we saying now? If I take a free unit positive charge, if I leave an unit positive charge here in this, in which direction or along which path it moves, that is the graphical representation of that is the line of force. Like suppose here the unit positive charge is here, and you have the positive charge, there is repulsive force, thus it moves like this. So all these lines, like these lines of force, move outward, radially outward. Here it is radially outward when it is a single charge present here. And now when you come to negative charge, right? So if you leave an unit positive charge here, right, an unit positive charge which is free to move, like when we don't discuss about any other kinds of forces acting on this here, where we talk about only the electrical force, that is the force due to this charge, then this is pulled towards it like this. So therefore this is the path covered by that unit positive charge, right? So therefore the lines of force for a negative charge are radially inward. They are radially inward. So here though you feel like it is a two-dimensional one, but now see, it is like it is having a spherical symmetry. The field here will be of spherically symmetrical about the charge, around the charge. Now, when it comes to the distance, see, when the area through which these lines of force either entering or leaving, if you consider, right, if you consider, then the same amount of the area if you draw, like, so you can see that the number of lines either entering or leaving this particular area is different at different places, isn't it? Different at different places, and the number of lines either entering or leaving, so these we call directly, very simply, very straight away saying, we call it to be flux, electric flux. That means the lines like that are passing through this area, and that flux per area we call, like, we define it as intensity of the electric field or strength of the electric field. The more the lines are, the more the strength is. That means here, like, very near to the charge, the electric intensity or electric field intensity is more, and as you are moving away from the charge, the electrical field intensity decreases, and at infinity it becomes zero. That is what we usually talk about electric field, right? Now, when you take like two positive charges which are like located near to each other, right? This is how the lines of force will be. Like, you can see that these lines of force, that means here they are like rippling each other almost, right? So here between these two charges on the line joining these two, there will be a null point formed. What is meant by null point? Very, very easy. Very clearly you know that null, in the sense it is zero. It is a point where electric field is zero, where the magnitude of electric field is zero. That means that point is called null point, right? So at this point you don't have any kind of electric field. And similarly, when you take negative charges also, which are located near to each other, then you can see that there is a null point formed here in between, and this is how the lines of force will get deviated. Like, see, because of the influence of the other things, you can see that there is a tension in the lines of force, and thus they bend. Instead of like being straight lines radially outward or radially inward, you can see that these are curves, right? So it is because of the tension, because of the neighboring charge, right? So these lines of force are under tension because of the neighboring charge. And now when you talk about like a dipole means it is something like when two charges of equal magnitude, but absolutely of opposite sign, are separated by a fixed distance, we call it to be a dipole. Just like to make you people realize that this is a dipole, I just drew it like this, but it doesn't mean that there is a charge inside here and inside here. It is something that two charges, right, which are separated, right, by a fixed distance, and of course the magnitude of the charges must be the same and the signs must be opposite. And such a case we call it to be dipole. And if we say that any other two charges also, if you take like one positive charge and one negative charge, lines of force will be like this, because if you leave a unit positive charge here, it will get repelled by this in this direction, right? And it will get attracted by this in this direction. Now see that there are two vectors acting on this, or the two forces acting on this, and thus it tend to move in a resultant direction. So that means this is the line of force here. This is the line of force. This is how usually lines of force can be drawn. And now as you can see that this is the direction, that means at this point you can see, if I leave a unit positive charge here, there will be a repulsion in this direction and there will be an attraction in this direction, and thus because of these two forces, now it is the resultant acts along the tangent drawn to the line of force at this point. So therefore, these lines of force, that means the tangent drawn to the line of force gives you the direction of the electric field strength, where electric field is a vector quantity, which is E bar, which is the force acting on, net force acting on a unit positive charge, which is placed in an electric field. Suppose here it is electric field created by two charges. The electric field can be created by one single charge or two charges, or even can be from by multiple charges also, right? And now when multiple charges are there, like, and then at a particular point, if you wanted to find out what is the intensity of the electric field, you need to find out both. One is magnitude and the other is direction. When you talk about magnitude, you will find the resultant force acting on that, and then you will find the magnitude, and the tangent drawn to the line of force gives you the direction of it. Or you can multiply the magnitude with the unit vector in that direction, then automatically you will get E bar. So E bar, talking very briefly, E bar is of course force experienced by what? Force experienced by unit positive charge, which is left free to move in the electric field. So that is how you say. That means here E is a vector quantity. It has direction and magnitude. So everywhere, whenever you draw a tangent, right, drawn to the curve, gives you the direction of the electric field at that particular point. Now you can see that, see, everywhere the intensity of the electric field is changing. So these are all non-uniform fields. All these are of non-uniform fields where the direction is changing at every point, right? And you can see also the magnitude is different, because you can see, like, here till now we did not discuss about how to find out absolutely, like, what is the electric field strength magnitude. But here, from the previous concept, whatever we have studied here, that the intensity is very high when it is very close to it, right? That means intensity is changing. That means magnitude is changing. As we are moving away from the charge, magnitude is changing. So thus, you can say that both magnitude and direction, if both are same at every point, then only we call it to be uniform field. If not, it is called non-uniform field. So all the examples whatever we have seen till now are of non-uniform fields. So when you talk about the field between two parallel plates, right? So this is positive and this is negative. So here the field which is between these two plates is uniform. You can see that the direction is same and intensity will be, like, you can find out the intensity at the midpoint, that is going to be the same. Like, see, this is how you can talk about the uniform field created here, right? And now here, if you say that there are like positive and negative charges both, like, where will the null point be? Suppose if we discuss, like before in the previous case, you can see that when two similar charges are separated by a certain distance, you can see that there is a null point between the two, like on the line joining the two charges, right? So now where will be the null point when there are two dissimilar charges? So now if you observe the lines of force here, like if the charge Q1 is of higher magnitude than Q2, that means the influence of this is more than this. That means the line of force which are like try to move like in this direction will slightly will be pushed towards minus Q2. But the influence of this is less, therefore they continue to be like this. So therefore at every point you can see that if the lines of force are here in this direction, and if you extend this is the direction. So both are opposite, like so towards Q2 it is coming, and this is going away from Q2, right? So now if I talk like if we discuss about the lines of force because of this, so this is only because of negative charge, it is into, and because of this positive charge you can see that the lines are like moving like this. So in this particular area we will get null point here. Null point means the point where the directions are opposite to each other, or where the electric field strength is going to be 0. If you observe it carefully, right, at this point you can see the null point. That is when Q1 is greater than Q2. That is the magnitude of Q1 is greater than Q2. If suppose Q2 is greater than Q1, then somewhere here on the other side of Q1 you will have null point, right? So please pause for a moment and note it down. Now to find electric field strength, magnitude of electric field strength first. It is the force experienced by unit positive charge. Okay, let me imagine that Q is a charge. Like, so here whenever we talk about this one, no, please remember that these are all point charges. Because why? Because we are applying Coulomb's inverse square law. And already we discussed that Coulomb's inverse square law can be applied only when the charges are of point charges. Right? So now here this is a 1 point charge with magnitude capital Q, and there is one more charge plus 1 here. Right? So now yes, plus 1 here. Now the distance of separation between them, if it is D, distance of separation between them is D, then what is the force on this? Force is equal to E into 1 by 4 pi epsilon naught Q into 1 by D square. If it is especially on unit positive charge, that force itself we are equating it to electric field strength as per definition. Right? So that means force acting on a particular charge Q1 because of Q is 1 by 4 pi epsilon naught into Q by D square of unit positive charge on unit positive charge. Let's suppose if you imagine that there is a test charge here. That means you are going to test like what will be the force on this charge. Then what is the force? Force is 1 by 4 by epsilon naught Q1 Q2. Here Q1 is capital Q, Q2 is Q naught. So by D square. And now this whole thing, right? This whole thing, this is E. Already you have defined it to be E. So therefore E is equal to this quantity E is equal to F by Q naught, then F by Q naught. So that's the relationship between electric field strength and the force. Okay, right. So suppose if you have a test charge there, find the force first and then divide it with Q naught, you will get E. Right? So this is the relationship between force and force and electric field strength, or rather most famous equation, like how you have F is equal to ma and all that, like that you have F is equal to EQ naught. F is equal to EQ naught. Very, very, very important relationship. Very, very important relationship. Suppose if acceleration of this is asked, that means when the force is acting, when a force is acting on any body, so either the body tend to move, right, or it moves, right? Either it will try or it moves. So therefore there will be obviously some acceleration, maybe zero acceleration or maybe a non-zero acceleration. And if at all acceleration is asked, what is acceleration is equal to? A is equal to F by F. In the upcoming classes you will be discussing about this, and where you will see many applications based on this concept. So this is very, very important relationship. F is equal to EQ naught. Right. So now the same in terms of vectors. Why? Because E bar, E electric field strength is a vector quantity. So therefore, when you talk about electric field strength and force, that is a vector quantity. So thus we have to give the vector representation of the situation. Let's suppose there is some charge Q here, a positive charge Q here, and at a point P I wanted to find out what E is equal to. If I want to find out what E is, I need to imagine a unit positive charge here, and the force acting on this because of this is E. So E is equal to 1 by 4 pi epsilon naught Q into 1 by R square. Right? So this is the magnitude part. This is the magnitude part. right, where into r cap by multiplying the unit vector in this direction. What is the unit vector in this direction? R cap is equal to r bar by modulus of r bar, right? So when you multiply this unit vector to this magnitude, then you will get the vector form of E, right? Or r cap is equal to r bar by modulus of r bar. Modulus of r bar, simply we will write it as r. So therefore now it can be r bar by r. R bar by r means r square into r is r cube. So therefore either you can write in terms of unit vector like this, or in terms of the vector which is given here is 1 by 4 pi epsilon naught q by r cube into r bar, where r bar is the position vector between these two, right? Between these 2 points, or the position vector of this point. And now take another situation where the charge is not at the origin, right? Here you have taken the charge to be at the origin, therefore this is a position vector and you are able to do it directly like this. Now suppose that the charge is somewhere here in the xy plane, or in the Cartesian coordinates system, where the coordinates are x2 comma y2 comma z2. And now the point of my interest, where I wanted to find out the electric field strength. So here I imagine a unit positive charge, and this point is at x1 comma y1 comma z1, right? So this is the position vector of this point, which is r1 bar, and r q bar is the position vector of this one. What is the position vector here? You know, from vectors you have learned that one, x1 I cap plus y1 j cap plus z1 k cap is the position vector. I'll write it here. So x1 I cap plus y1 j cap plus z1 k cap is a position vector of this one. Now if you take this one, it is x2 I cap plus y2 j cap plus z2 k cap is a position vector rq bar. Now the point here is that we want the distance between these two, is it not? So when I want the distance between these two, I should know what this vector is, and this vector is rpq bar, that is rp bar minus rq bar. It is rp bar minus rq bar. So now rpq bar is rp bar minus rq bar, right? So now what is rp bar minus rq bar? So this is the what do we say? P point P, right? So therefore rp bar minus rq bar is x1 minus x2 I cap plus y1 minus y2 j cap, and so on, right? So this is the rp bar minus rq bar vector. Now I want electric field strength in this direction only, no? Is it not? This is the direction of electric field strength. That means I want this particular vector. So now first of all, let us write down the magnitude part. That is 1 by 4 pi epsilon naught q by this square, the distance square. What is the distance square? Mod of this whole square. Mod of this means mod of rp bar minus rq bar. Whole square. First we will imagine it to be square here, into the unit vector in this direction. Unit vector in this direction is the vector divided by its magnitude. Vector divided by its magnitude. Magnitude is again mod of rp bar minus rq bar. So power 2 plus 1 again 3. So therefore rp bar minus rq bar whole cube. So this is the vector form like in case of position vector. So when the coordinates are also given to you, you can substitute the values here, and finally this is how you can find out the vector representation of electric field strength when position vector of the charge and the position vector of the point where you wanted to find electric field strength are given. Beautiful. Okay, right. So please note it down. Now the next topic is electric field intensity at a point due to multiple charges. So as you have seen, like you can write it into like for every particular charge q, there will be a field. Therefore, there will be an influence at a particular point because of the field. So individually, number of fields will be there in that, and we are going to find out the net field. It means number of forces will be acting, and you are finding the net force. And at the point, what you have to imagine? Yes, unit positive charge. So suppose at this particular point, I am imagining unit positive charge, and I have multiple charges here surrounding it. So Q1, Q2, Q3, Q4, where the vector distance is R1 bar, R2 bar, R3 bar, R4 bar. So these are the vectors uh, representing the distance between these two. Right. So now if I wanted to find out the electric field strength at this point, I need to find out the electric field strength due to every individual charge. Let me write it as E1 bar, E2 bar, E3 bar, E4 bar. So then E bar is equal to some vector sum of all these electric field strengths. So what is this one? E1 bar is 1 by 4 pi epsilon naught Q1 by R1 cap by R1 square, or Q1 into R1 bar by R1 cube. In both the manners you can write, is it not? Yes. Therefore now in the unit vector form I am writing and taking 1 by 4 pi epsilon naught common everywhere. So this is how I can write Q1 by R1 square into R1 cap plus Q2 by R2 square into R2 cap plus so on. Right. And now the same can be written as like summation of that. So sigma I is equal to 1 to n qi by n ri square, qi by ri square into ri cap. Or in place of ri cap, if I write it as ri bar, right, ri bar by modulus of ri bar, that is ri. So Ri into Ri square will become Ri cube. So therefore, this can be the other way around if you wanted to write it indirectly in terms of a vector. So now therefore at this point, this is the electric field strength, and this electric field strength is because of multiple charges. Clear? Right. So now the same if position vectors of the different charges are given, right? That means where the charges are located, right? So let me say that this is Q1, this is Q2, right? And this is Q3, and this is Q4. I have charges Q1, Q2, Q3, Q4. That means these position vectors of these are given in the sense where this is located with respect to the origin are given. That is R1 bar, R2 bar, R3 bar, R4 bar are given to us. And now at this point I wanted to find out the electric field strength. And now for this the position vector of this point is R bar, let us suppose. Now what is the distance between these two? It is the magnitude of the R bar minus R1 bar. That is modulus of R bar minus R1 bar. So that is, and now here if you want to define the distance between these two, R bar minus R2 bar, modulus, and here modulus of R bar minus R3, here it is modulus of R bar minus R4. So this is how we will find out if at all position vectors are given to us. So therefore E bar is equal to 1 by 4 pi epsilon naught Q1 by R bar minus R1 bar modulus whole cube into R bar minus R1 bar, right, plus Q2 by R bar by R2 bar modulus whole cube into R bar minus R2 bar plus so on. Right, so this is how we are writing it in the vector form, and in the simplified form or in the summation form, Qi by R minus Ri bar modulus whole cube into R bar minus Ri bar. Right, so this is about electric field strength due to multiple charges. Here there is an important point for me to discuss with you. So these charges are distributed around this point in a discrete manner. In the sense these charges are not continuously distributed. These charges are not continuously distributed, right? But whereas continuous distribution of charge, that is a different concept. So we will learn that in part 2 of electric field strength. Right now, so we are talking about how when there are charges scattered around a particular point charge. So these are all point charges. No, here we are not going to talk about like a charged ring or a charged sphere or a charged plate. We are not talking about that. We are only talking about here point charges, and the charge distribution is discrete around the point, right? So this is what, which is very very important conceptually, you should remember that, right? So now the next part here is like how is the variation of electric field strength. How is the variation of electric field strength graphically? How do you represent it? Now suppose if I take a positive charge, because of the positive charge, right? So how the electric field is here, whether it is a positive charge or negative charge, you can see that E is inversely proportional to the square of the distance, is it not? Like how, as you are moving away from the charged body, like then E is inversely proportional to R square, or E is proportional to 1 by R square. So therefore this will be the curve, right? This is how the curve will, when E is greater than 0. When E is greater than 0, here you can see that as x tends to 0, right, E is like what do we call infinity. E is infinity, and as x is increasing, as the distance is increasing, you can see that electric field strength decreases, and yet infinity, x is equal to, or means x is tending to infinity, E tends to 0. This is what we have learned theoretically till now, is it not? Electric field exists around a charge and it extends till infinity, and theoretically we say that at infinity only electric field strength becomes a 0, right? So when E is less than 0, this is how the graph will be, right? This is for a positive charge, and the same conditions now have under the same situation. If you observe the graph, this is how the graph will be like for variation of electric field strength when it is with due to negative charge, that is when E is less than 0, and here this is for E greater than 0, right? This is very very important, because after these things, like after we discuss the theory, then we also solve the problems based on like how the behavior of E will be. Like at that point you should know how these graphs will be, like why we are getting such a resultant graph. And in IIT JEE also, graphical analysis of the problems is very very important. So you will be finding a question like where you can see that which one is this and which particular condition does this graph represent, right? So please make a note of this one.